A small block of mass m starts from rest at the top of a frictionless track at a height h above the ground. The track leads into a vertical loop of radius r, where h is greater than 2r. So that just means that the block starts higher than the top of the loop. Assuming the block remains on the track unless the normal force becomes 0, determine, in terms of h, r, and g, the minimum value of h required for the block to maintain contact with the track at the top of the loop. So first, let's just think about what this condition is. It wants the block to maintain contact at the top of the loop. And it says that the block remains on the track unless the normal force becomes 0. So maybe it might help to draw a free body diagram first and visualize what would be happening to the block as it travels along the loop. So suppose this is the top part of the loop, and we want to ensure that the block remains in contact with the track at the top of the loop. So if it's in contact, the normal force is non-zero. So we're going to have a normal force that's normal to the surface and pointing downwards, since it's traveling in the inside of the track. So it goes from here and then travels into the inside of the track and then travels back out. And in addition to that, we also have the force of gravity, which is just the block's mass, m times g. So now the total forces on it in the y direction are n, the normal force, and the force of gravity, mg. And since this is a circular track, the sum of this force must be equal to the mass times the centripetal acceleration, which is, since this downwards direction is also in the radial direction, it points directly towards the center of the circle of the track, or of the loop. And the centripetal acceleration is just v squared over r. So we have this equation here. And it might be more clear if I remove this middle part here. And now our condition is that it must remain in contact with the track. In other words, the normal force must be greater than 0. So maybe we can rearrange this equation and solve. Let's start by solving for the normal force. So the normal force is equal to mv squared over r minus mg. And we established that it must be greater than 0. Okay, so now we have something in terms of v squared, but we don't know what that actually is at this point. And that's the second part of our problem here. So maybe we could either use like Newton's laws and compute the acceleration and then use that to find the speed, velocity here, or we could use energy conservation. So if we think about using Newton's laws, notice that the instantaneous slope of this track changes at each moment. So that means our acceleration is not constant, and we can't use our constant acceleration kinematic equations easily. So instead, maybe we should think about using energy conservation. So if we define the bottom of the track to have a y value of 0, so maybe this is y equals 0, then recall that the gravitational potential energy is equal to mgy. And it doesn't matter what the actual value you define y equals 0 is. It only matters the difference between the values of y. So if we define this y value to be 0, then this block would start at y equals h. And at this point, it will have a y value of 2r. And so now we can just use energy conservation. And it's on a frictionless track, so no friction acts on it, and mechanical energy is conserved. So that means that the initial kinetic energy plus the initial gravitational potential energy equals the final kinetic energy plus the final gravitational potential energy. Since the block starts from rest, this initial kinetic energy term is 0. And now we can just plug everything in. So the initial gravitational potential energy is just mg, and y is h at the start. And we can set that equal to the final kinetic energy is unknown, and it has a general formula given by 1/2 mv squared, where this v is the same thing as the v over here. And so perhaps we can solve for this v in terms of these other variables. And we also have the gravitational potential energy term, which is mg, and in this case y is 2r at the end when the block is over here. So mg2r. So now maybe we can solve for v squared and then use that to substitute into this equation here to find our constraint for what h must be, since we can solve for v squared in terms of h and all of the other constants that we were told to express our answer as. So let's start by canceling out all of the masses. And I could have done this in this upper equation as well. I can remove all the m's. And then let's solve for v squared. So let's subtract g times 2r from both sides. So we have gh minus 2gr. And that equals v squared over 2. And then we can multiply both sides by 2 to get that v squared equals 2gh minus 4gr. Okay, and then let me clear up some of this here. So now we have v squared. And so maybe we can plug this into this inequality here. So let me rewrite this for a little more clarity on what we have right now. So right now our condition is that v squared over r minus g is greater than 0. And now after plugging in v squared, plugging in this for v squared, we get that 2gh minus 4gr over r minus g is greater than 0. And notice we can cancel out the g's as well. And this, if we divide everything by g, and then this is going to be a 1. So now let's add 1 to both sides. So 2h minus 4r over r is greater than 1. Multiply both sides by r. And then we can add 4r to both sides. And our final answer is that h is greater than 5r over 2. And so this implies that the minimum h required is just simply 5r over 2. And that is how you would solve this problem here.